Okay, cool. So election side, we have computational work, a little bit more in our control, not as hectic. I mean, still can be frustrating, but not as frustrating as politics. And yeah, more of the same. We're kind of working through the linear algebra work, and from what I've seen, people are kind of chugging along. I haven't seen too many issues come up, so that's pretty cool. Any concepts or problems to get started on? I think last time I was helping troubleshoot somebody with like linear regression kind of work, but I don't know if everyone is up to that point or if we're at different stages. Yeah. Oh, how to get started on it? So I'm scrolling down, try to get there. Do you want to look at the symmetric one where we just have like one reaction force and two, like, so when everything's symmetric, R2 and R3 are equal, and then P2 and P3 are equal, so we only have to solve for P1, P2, and R2, or R1, but either way. So here we can set up really like these three equations that are in here are looking at like the X and Y components at three different locations in this triangular truss. So we're just taking sum of the forces equals 0 and solving all the equations all at one time. And for statics, like you could do this even for like big truss problem, like if you had tons of force, internal and external reaction forces. It makes setting it up a little harder. So if I can say like this matrix is a 1 cosine of, I'm going to say A and then type in the A after, a 0, a 2 times that sine of A, and a 0, and then a 0, negative sine A, and a 1. And I'll say that alpha angle is 75. Like that. And then my right hand side, like if I say AX equals B, B is going to be, let's zoom in some so we can see. That 0, F, and 0. And again, I'll set up that F. Start off as like 100. Yeah, n pi is not defined. Oh, and I guess, do we want to use, we're supposed to use that LU decomposition. So let's decompose it. What do I want to do? So in the reading, there's an LU naive function that will do, it's the same process as Gauss elimination. It's just that it's saving both the upper triangular matrix, which is like our augmented kind of output from Gauss elimination, but it also keeps track of what coefficients we use to create it. So then it creates an a lower triangular and an upper triangular matrix. It does save, so if you do this decomposition once, then the next time you solve the problem, it saves some time, like computer time. Doesn't necessarily save you personally time, but if you have like a smart linear algebra kind of problem, you decompose it once and then keep solving those problems as you're changing things. So that's what we're trying to do. So we can use this naive approach, or we can import an approach. Let's import it just to see what happens. So when I ask for the LU decomposition of A, because this SciPy LU decomposition does pivoting, it'll do partial pivoting so that the Gauss elimination doesn't run into errors. I think we saw that last time on Monday, but you end up with like not a number if you have zeros along your diagonal. But this first output is just a pivot matrix, so it's just keeping track of how Gauss elimination would rearrange rows, and then the next two are the lower and upper. So because I have diagonal all ones, it's an identity matrix, so there's no pivoting being done. So whether I use naive or partial pivoting, it's all going to give me the same answer for this problem. So I have, and the outputs there are a pivot, a lower, and an upper matrix. So the upper matrix would be that part of the Gauss elimination, the augmented matrix. All right, so now I want to solve two problems, and it usually helps me to write it out. So I'm saying AX equals B, but then I write out this I create a new problem where it's LUX equals B. So I'm going to solve it in two steps. Step one. Oh, why did it change color? Oh, the numbers change colors. Ah, cool. It's going to change my whole game. 9 is orange. So first I'm going to say L times, call it like Y, equals B, where this is Y. So UX equals Y. So then I can say UX equals UX equals Y. And it seems like we're making it more complicated, but it's kind of like when, yeah, and it does make it more, there's more steps to the solution, but each of these steps are very easy to solve because an upper triangular matrix is all back substitution and a lower triangular matrix is all forward substitution. So there's never like a system of equations. It's always one equation, one unknown for every row, which is kind of nice. And then if I had pivoting as well, I would have PLU X equals B, but I can get rid of that pivot and say P transpose times B. And then it's the same problem where I'm saying P transpose B is now going to be LUX. So this first step would be like that, P transpose B. So I'm writing this out, one, so I don't mix up the steps, and then also, yeah, again, it helps me to write things down on paper before I start trying to like code it. Sometimes that seems a little misleading because I've written this down on paper so many times that I know what I'm trying to do, but it helps to stop, think, what is the goal here? So I've got P and L. So I could just say linalg.solve. Oh. And I want L and B. And again, I'll call this like Y. And then X is going to be U and Y. Oh, and I should probably match the case. So kind of stepping through what I did, I turn a system of equations, this matrix, into actual arrays like numbers in the computer. Those I'm decomposing into L and U, lower and upper matrices. And now I can solve in that two-step of saying, all right, solve the lower matrix and then solve that upper matrix. And it's kind of taking that Gauss elimination and batch processing, like doing all of the Gauss elimination at one time for LU decomposition, and then the back substitution all at one time. So right now, if my force is 100, so I'm pushing this thing down, theta equals 0, 100 newtons, then my internal stress along P1, so the thing that's holding the bar 1, how much internal force there is in there. For 100 newtons, it ends up being negative 13 newtons. Do you know what it would be if it's 1,000 newtons? We could change the force in C, yeah. But do you know? Do you know what it would be? Yeah. 100, yeah, 133.9, right? 133.97. $133.97. So linear algebra equations, they're always linear. So if you multiply either side by one factor, all your answers are multiplied by that same factor. which is kind of nice because we're trying to plot this like every 10 newtons from 100 to 1100. I can do it in a for loop, right? Like I can solve this problem over and over. Let's say f equals yeah, let's take this one down here. What did I say? 1100? And make sure it has like a marker. I'm gonna call it, let's do red squares. Oh, plot is not defined, come on. Oh, that can't, oh yeah, I should multiply by f, right? There we go. So now I'm seeing like from 100 to 1100, it's always just a linear relation. The bigger the force, the bigger the internal reaction force is.
My code seems to be the same, but I'm getting just a really weird one. That's really, oh wait, I didn't get that one. Somebody put all the investment that I have. Yeah, all like all of their yeah.
Yeah, that's usually better, right? Yeah, straight line. There should be some reaction to this. Yeah.
So when we're solving for the LED composition, what is the result we're looking for? Because I get when you're solving for using Gaussian elimination to get your answer for the unknowns. Yeah. What is the answer when you're solving for the LED decomposition? Like, what's the final result you're expecting to see? The same thing as Gaussian elimination?
Yes. Yeah. So let's take a look at I'm gonna make this run my Gauss naive again. So if I'm looking at my upper triangular matrix versus my Gauss elimination augmented matrix, they're exactly the same because they both went through the same process to get to that upper triangular form. So by doing that extra like bookkeeping of keeping track of that lower triangular matrix, you're kind of you're doing Gauss elimination, but for any right-hand side equation.
So is that just the answer basically is the U output when you solve for the LU decomposition of A? When
Yeah.
you're saying solve for, what is it actually expecting to output?
Oh, so if you're solving for like
just to answer the question basically that it's stating, what is the output it's looking for?
For part B. Yeah. For part B, it's like we're actually looking for
the L and U matrices.
Yeah, like okay. L and U. That looks kind of ugly, but
because then if you were to multiply them together, you would get A.
Yeah, so L times U is going to be A.
Yep.
Yep.
Okay. Thank you.
So before I went through and just manually said, okay, solve this problem, what is it, 100 times? Yeah, solve the same linear algebra problem 100 times, but just keep increasing the force by 10 newtons. But if I already know that it's a linear problem, I could solve for f equals 1 and then just keep multiplying the result by whatever magnitude of f I need. And I should get the same curve if I don't have if I get rid of some errors. Now I get the same exact curve, like same exact straight line, because I'm just taking advantage of the fact that I know if I solve for f equals 1, I can always multiply the output by whatever value of f I want. This is a great, finite element methods are usually the same way, where if you're solving, like if you set your modulus as 1 and all your applied loads as like some ratio of like how close in the Young's modulus, you can have 50 different materials just by multiplying the outputs by a different factor. But, all right, now it's 1,000 times higher for a plastic or anything like that.
What is the function you used to call the LU decomposition? Because it comes from SciPy, right?
That one I grabbed from SciPy. This linalg SciPy LU.
The input for the arguments for the LU function is only the A matrix, right?
Yeah.
You don't care about the output matrix.
Yeah.
The output vector.
Mm-hmm.
So that's why you can't read the one there. It's still after the, and that's why we work out by FIN.
Yeah. Yeah, so I can say B times F is going to be plugging in a new value for that one. Not everything is nice and linear, but it is nice when it works out. Just say like. Bless you.
So it's just similar process, just more variables under delay.
Yeah. Yep. For here, I'm going to show like ChatGPT. You can give it the latex.
Yeah.
Okay. Yeah. So as we move into the next one, where we lose symmetry, now we've got three different angles, like the angle of force, the different truss angles, and all that. So it can be kind of cumbersome to translate that over into NumPy. Sometimes as you're trying to do it, you might switch a cosine for a sine or something like that. But you can like right click. MathML is going to be like an HTML version of that matrix. The tech commands would be like the actual LaTeX setup for those equations. But either of those are easy for machine reading. I need you to convert this LaTeX matrix equation into NumPy arrays. Oh. And so far, it's been doing pretty well. I don't know. I defined an array of text strings, but then I don't really. There's not really a reason to create a column vector versus just a one-dimensional vector, but it'll still work as long as this is 5x5, like 1, 2, 3, 4, 6x6, and then this has 6 values in it. And this is kind of useless because we're trying to solve for that one, but you probably play around with the prompt engineering to get it to look a little better.
Yeah.
Oh, I already typed it in there. I don't care for these. So if you're trying the next step and you run that Gauss naive method, without doing any like pre-processing of the work, you're probably getting a whole bunch of not a numbers and infinite values. Our output is all just not a number. Something's weird with that naive Gauss elimination method. And even if I tried that LU naive to like do the lower upper triangular decomposition first, it would still give me this, because in the very I'm gonna go back up. In the very first step of this loop, oh wait, is this? Yeah, we're using the diagonal values, that augmented of kk, and dividing it by all the first values or like just using that as a factor to like get rid of the rows below it. But our first diagonal element is 0. So immediately it's going to like cascade through a whole bunch of divide by 0 error, or at least warnings. If it's pink, it's just a warning. So it's telling you like, hey, I did what you asked me to, but it's probably not what you're looking for. But again, there's no reason that that has to be our first equation. Like this doesn't have to be equation 1. I could say, no, you've been demoted. You're now equation 2 because you're giving me issues. And now when I run that same command, Gauss naive, I get a bunch of outputs and my augmented matrix looks like pretty reasonable. A whole bunch of numbers. No longer like not a numbers and infinite values. And the only difference was that I did a little bit of partial pivoting. Really, I switched that 0 with the 0, but didn't actually do anything because first two equations both equal 0. But just take those two first rows, flip-flop. And if we want to know like what the actual let's bring A, let's put A back to what it was before. So if I look at like how LU decomposition with a little bit more advanced thought process, because usually it's trying to find, it has a certain criteria of like what the diagonal it wants for that augmented, but it does take row 1 and row 2 and switch them. That's what that 0, 1 and 1, 0 are. It's like taking those first two rows and switching them. And then it also starts switching around. It looks like it leaves row 5 alone, but then row 6 becomes row 3. Like it just kind of rearranges all those things. And if you just look at L at U, kind of hard to tell what it is, but it's the pivoted A matrix. Yes, I have to use a is close. There we go. Is it P transpose? There we go. P transpose at, so LU is P transpose A. Yeah, I was trying to remember how it works. So PLU is LA, or P transpose A is LU. equals doesn't work so well. Yeah, equal, because if it's just off by like 1 bit, then technically it's not the same, but is close is a good way if you're looking for something. And you can even specify like how close you want it to be. R tall, A tall. Oh. There we go. That was bugging me. It kept giving me errors. But if you're trying to figure out like, are two things, like are two arrays, do they have the same values in them, or are they all the same? Usually is close is better than straight up equal sign, unless you're looking at like integers. But for floating point, usually is close is a better way of measuring. Are these roughly the same? Or imperceptibly the same, because within 0.0001 is, I think it's 0.0001%. I think the R tall is measured in percent. Relative tolerance. Okay, so this is within 0.01%. So times 100 to get a percent number. Is that our time? Yeah. Time flies. All right, have a great day. I'll see you again on Friday.